My name is Marish Postol. I want to invite you to participate in the next lesson of the External Data Management course. It is part of the educational path called Programming in Practice. Programming in Practice is a discipline that systematically applies engineering principles to the design, development, and implementation of algorithms, program text editions, and testing. It is a part of the software engineering discipline comprising sequential, adaptive, concurrent, real-time, and distributed programming. It also includes external data management. The primary objective of this lesson is to introduce the concept of anonymous functions in the context of external data management. Hopefully, I will keep the discussion broad enough to be useful and applicable despite the main focus. To make it practical, all examples are prepared using the C# programming language. Learning about anonymous functions can be motivating for several reasons. By design, anonymous functions enable more concise and readable code, are a key part of functional programming, and are widely used in event handling and link queries. They can reduce the overhead of creating separate named methods. Many popular frameworks utilize anonymous functions extensively, as do the following examples. As usual, let's start by defining the main objectives of this lesson. By defining the topics we may encounter in the context of anonymous functions. The primary fundamental issue is the meaning of the term anonymous function. In software engineering, we use procedure, function, and method to refer to a parameterized sequence of instructions. By design, a procedure is a parameterized sequence of instructions that performs a specific task by applying provided parameters. It does not return a value. It can be recognized as a custom structural statement. The function is a similar language construct to a procedure, but is designed to return a value as a result of execution. Hence, in the sequence of instructions there must be a return instruction ending the sequence execution and returning calculated values. Methods may be recognized as a programming language construct using both roles, namely a function or a procedure. In strongly typed languages, if a method is used in the procedure role instead of returned value type, a special keyword is used, for example void. All of them are defined in declarations associating the definition with a name unique in the selecting context. For procedures, an invocation statement may be defined by a programming language. Functions may be used as co-operands in expressions. If there is no declaration associating a name, the structural statement must be recognized as anonymous. To be invoked instead of a name, a reference pointing to the structural statement must be used. In this context, we may talk about anonymous procedures, functions, or methods. Hence, the anonymous function term sounds confusing. Using anonymous functions, we may expect the benefits mentioned previously. Unfortunately, all are true, but no one is directly related to external data management. Hence, this issue must be especially addressed during this lesson, even at the expense of a detailed description of the concept. External data requires storage and retrieval resources controlled by a domain-specific language. A programming language should enable management and query of external data repositories in an integrated and unified way, allowing developers to perform operations like deleting, inserting, updating, and retrieving data without the necessity of learning this domain-specific language. It is the next problem that must be addressed. Anonymous functions, also known as lambda expressions or anonymous methods, are parameterized sequences of instructions that do not have a specified name. They are allowing for more concise and flexible code. The concept has evolved, with lambda expressions gaining popularity over traditional anonymous methods. Anonymous function is a key contribution to functional programming, and it cannot be omitted in the context of language constructs supporting the management of external structural data. They are also vital for implementing internal communication using type-safe parameter structural instruction invocation, for example, delegates. Considering both arguments, it is clear that the delegate concept must be investigated in detail as a part of the introduction describing selected language constructs implicitly contributing to the anonymous function. As an introduction to anonymous functions, let's examine the anonymous functions example, which comprises the usage of delegates for the named method. The examined code snippet is also used in the case of anonymous functions. It is an implementation of a well-known state machine or design pattern. Despite this class functionality, to check the instance consistency, the consistency check method is declared for testing purposes only. It is declared within the anonymous functions class. It is preceded by the conditional attribute, because the conditional check method is defined for testing purposes only, and the method should be removed from the code if the testing is not the main goal, for example, in the case of the production code. This attribute indicates to compilers that the method call should be ignored unless a specified conditional compilation symbol is defined. More precisely, applying conditional attribute to a method indicates to compilers that a call to the method should not be compiled into executable code unless the conditional compilation symbol associated with conditional attribute is defined. As a consequence, the method must not return a value. To return a test result value, the callback notion is used. To implement the callback notion, a delegate comprising a reference to a method is to be created. The testing code sample is located in the anonymous functions unit test class. The anonymous method called backtest method creates a delegate comprising a reference to a named instance method of the callbacktest class. The callbacktest class reference type is declared in the instrumentation region. The callbacktest result method is used as a callback to return a test value assigned to the m_test result local field. In the named method callbacktest method, a delegate value is created for the callbacktest result method after instantiating the callbacktest class. This delegate is used as an argument of the consistency check method to return a result for testing purposes. Next, we will examine how to implement similar functionality using anonymous functions in the context of the expected benefits. In the next step, let's check how a similar functionality can be obtained using anonymous functions. We will pay special attention to readability and the possibility of making the code more concise. The readability improvement will be achieved if scrolling is not required to read the relevant code. We will also judge how the anonymous functions impact the conciseness of the code, measured by the length and compactness of the text. Let me remind you that an anonymous method is one of the kinds of anonymous functions. The example of an anonymous method definition is located in the anonymous method callback test method. We have a delegate variable declaration on the left side of the following line. Alt F12 will remind us that callback test delegate is simply a delegate type. Here, the underscore callback test result is a delegate variable to which we assign a value in the form of a reference to a set of methods compliant with the declared type. In the sample code, the set contains only one member, a reference comprised by the created delegate, pointing out a method is evaluated for the expression to the right of the equal sign. For such a definition, we have a list of parameters, and of course, we have a block, that is a sequence of instructions executed when the method is called. The above code snippet, for example, is the assignment to a local variable instruction. Since we do not have a name associated with the method definition, we call this an anonymous inline declaration, anonymous. This declaration may be more concise because it contains only a method definition. Additionally, let me stress that there is no need to scroll to analyze all dependencies. As a side effect, this definition may be embedded in expression text, which defines code elements directly within the context where they are used, rather than separately. As a result, the text is more compact. The penalty of using the anonymous methods is that we cannot refer to them in any other way than by using the delegate variable. Note that the delegate variable has a name, so it is not that we cannot invoke an anonymous method using a name. Always the name must be used. Of course, the difference between invoking a method directly using its hard-coded name and invoking using a delegate variable leads to the possibility of the assigned value to a variable change. This way we are dealing with a kind of polymorphism without the necessity to apply object-oriented programming. The polymorphism term itself means many forms. It enables using common definitions of a method header to represent different implementations. Finally, we can recognize this approach as more flexible. If we compare the definition of a name method, here we have just such a name method, with the definition of an unnamed method, here is such a definition, we can see that the difference is only syntactical. In subsequent programming language versions, further simplifications have been introduced, allowing this definition to be shortened and written in a different text form. One difference is that an unnamed method has access to local variables defined in the method in which it has its definition, but this results from the place where it is defined. It is an example of an inline definition. Let's move on to the next incarnation of anonymous functions, the lambda expression. Here, using an anonymous function, the lambda expression complements the same functionality as before. Using the lambda expression, I want to remind you that nothing has changed in this method compared with the anonymous method above. What is written as an expression on the right-hand side of the equal sign is simply an operation instantiating a delegate object comprising a reference to the method defined using lambda expression syntax. This method implements the same functionality as before, with the same list of parameters. The only difference is that a new syntax is used to implement it. Moreover, this syntax can be further simplified. For example, the type of parameter could be dropped here. In this scenario, the compiler must infer this type, of course, knowing the definition of this delegate type, prefixing the variables there is no problem in guessing this type. So again, comparing the definition of an anonymous method with a lambda expression, we can conclude that only the syntax is different. The delegate variable is still a formal parameter, hence the current argument must be an instance of an object wrapping a reference to a method with a compatible signature. The lambda expression has a syntax form where the equals greater than operator separates the list of parameters and the instruction sequence. For the sake of simplicity and to make the lesson time short, we must skip details related to the syntax details. Check out MSDN Learn documentation to get more details in this respect. Sometimes it is difficult or even impossible for the compiler to infer the types of formal parameters. When this occurs, you can specify the types explicitly, but leaving these details aside, in the lambda expression blower method, we see an example of creating a delegate value comprising a reference to the method expressed using lambda syntax. In this code snippet, we can distinguish a list of parameters and a block. In this code snippet, the expression text, the right-hand side of the assignment operator, is more concise because a delegate object is created implicitly even without a new operator. The created delegate value is assigned to the underscore test local variable. The associated value of this variable is used as the current argument of the formal parameter of the consistency check method. It is defined within the anonymous functions class and is used to check the internal consistency of its instance. Here we have an assertion that checks whether a local variable changes the value to true as a result of the callback of the anonymous function. It means that the method referenced by the delegate has been invoked by calling the consistency check method. Thanks to the inline declaration, we can rely on the side effect and directly assign a value to the underscore test result local variable, invoking the method defined by the lambda expression. Based on the above examples, let's return to the question of what the term anonymous function means. To be honest, I don't know where the name anonymous function came from. I can only guess. But let's try to answer this question based on common sense. Here is the definition of an anonymous method, where the delegate keyword may be recognized as the name of the compile time operation of creating a delegate value. If we interpret the keyword delegate as the name of a compile time operation, the right side resembles the function notation where a delegate value is created. In other words, the delegate keyword is used to instantiate and return a delegate value comprising a reference to a parameterized structural statement that is defined as a right-side construct of this keyword. We can also apply the lambda expression syntax to define the parameterized structural statement as in the lambda expression commander and test. We can define procedures or functions independently of applied syntax without directly associated names. In this concept, the typical method declaration associating an identifier with a parameterized instruction sequence is replaced by an assignment instruction. As a result, a reference value contained by a variable can be used instead of a hard-coded, parameterized structural statement name. There is another outstanding question, namely, what is the reason for all these syntax changes that I encountered in the context of the anonymous functions? Why do we need another syntax construct of the same functionality that we had in the anonymous method correct method set? The basic question is still unanswered. What's the point of all this? Let's try to answer this question in the context of external data management. If data must be recovered from an external repository, the operation describing the operation that is to be applied to this data must be executed by an external system. As a consequence, a functionality expressed in terms of selected programming language syntax instead of local execution must be translated to a domain-specific language to be useful and executable by the external system. To make the translation feasible, this functionality must be syntactically embedded in an expression, a sequence of operators and operands. Before translation, it must be expressed using the object model in the form of an expression tree. To make this process effortless, the expression tree could be created automatically by the compiler. To create expression trees manually by using the API, Use the expression class. This class contains static factory methods that create expression tree nodes of specific types. Details you can learn from the expression trees conceptual documentation. The code sample based on compiler usage is located in the anonymous functions center. That's to follow me. Scroll to the delegate defs expression test method. Unfortunately, the compiler can generate expression trees only from lambda expression or single line lambdas rather. We can observe a change in the following code sample in the delegate defs expression test method. Again, we have a lambda expression on the right side. On the left, we have the definition of the lambda variable, but this time this variable is not a delegate variable as before. This variable is of the expression type. It is expected that after executing the expression, a compatible value will be assigned to this variable. It should be a reference to an instance of the expression class. But according to the entry on the right side, we should create a delegate value comprising a reference to the message written this time as a lambda expression. The delegate type is not compatible with this reference type. It is the place where the fundamental difference has been encountered. Because in this case we do not create a delegate value, that is, we do not create a reference to a method. It means this expression will be represented by an object of type expression class, and a reference to it is assigned to the lambda variable. So instead of executing the expression, the compiler translates it and represents it using an object form. It is possible only when the syntax of this expression is appropriately simplified. Let's look at the example below. Well, when we change the lambda expression to a slightly more complicated one, but still correct, equivalent, and consistent with the lambda expression syntax, the compiler is incapable of realizing this translation. For example, I copy a code snippet from the code above. It contains an equivalent lambda expression that was not complained about by the compiler a few lines above. Note, if you are creating expression trees that are executed outside of the .NET framework, such as in SQL Server, you should not use method calls in lambda expressions. The methods will have no meaning outside the context of the .NET Common Language runtime. To make the translation possible, all side effects must be omitted because the expression is to be executed in the context of an external data source, but not in the context of the program by design. This requirement is well suited to be addressed by the functional programming style. That's all for now. Thank you for watching. To follow me, watch or start the repository with extended examples on GitHub. If you have questions or doubts, contact me by Gmail at programminginpractice24. Let me invite you to visit my profile on C# Corner. Details can be found in the lesson resources. Again, thank you for your time. I look forward to seeing you again during the next course, which will focus on structural data.